Welcome to the Tech Talk today, everybody. I published an internet app. Wait, how do I protect it? So today we're going to dive into what the considerations are and tools you need to protect your internet-facing applications on AWS. I am Nick Koval, Principal GTM Specialist with AWS, and today I am joined by my esteemed colleague, Tom Adamski, who's a Principal Solutions Architect here at AWS. All right, so today we're going to open up by reviewing the NIST Cybersecurity Framework, which is a good framework to help us contextualize our risk management strategy to make sure that we're thinking holistically about how to protect our assets in AWS. Next, we're going to go through 3 protection use cases, and this is how the 3 different ways that traffic crosses network boundaries within AWS that contextualize it, how to think about the tools to use to protect your assets and the traffic that's flowing between them. Then lastly, I'm going to cover defense in depth strategy that helps us look at the variety of AWS services that we can use in a defense in depth approach to protect our assets so that we're thinking holistically with a layered approach to protecting our assets. Then I'm going to hand it over to Tom. He's going to go through our foundational constructs. These are some of the fundamental techniques that you'll benefit from by understanding, such as VPC routing and how some of our load balancing services work in AWS. That's important to know as you're building out these reference architectures. And then finally, Tom is going to do a deep dive into a variety of network architectures that's going to show you exactly how to put into practice these techniques and best practices along with the AWS services that we talk about to adequately protect your internet-facing applications. All right, so to get started, the NIST Cybersecurity Framework is voluntary guidance based on existing standards, guidance, and practices for organizations to better manage and reduce cybersecurity risk. In addition to helping organizations manage and reduce risks, it was designed to foster risk and cybersecurity management, communications amongst both internal and external organizational stakeholders. The framework is designed for any and all organizations, regardless of sector or size. And so it's broken down into 5 different components or phases here that I'm going to walk through to give a high-level overview, not comprehensive, but high level, and then talk about how it can fit into the AWS environment. And there is a QR code here on the bottom that will link you over to the NIST website so you can learn more about the cybersecurity framework at your convenience. All right, so first, what processes and assets do you need to protect? This is where you go through the mechanism, the process of trying to understand what assets you need to protect and what are the risks and vulnerabilities that you want to build a strategy for. Next, what safeguards are available? These are the tools that you want to implement within the environment to actively inspect and protect the traffic that's traversing and heading towards your workloads. Next, what techniques can identify an incident? Let's just say an incident were to occur. How do we make sure we can detect that and then move forward to remediating the situation? And so after we detect it, what techniques can contain the impact of the incidents? So this is as we're building our automation to handle response and making sure that we contain any of the artifacts that are a result of any sort of incidents that were to occur. And lastly, what techniques can actually restore our capabilities to bring us back online in a recovery and to bring us back to recovery phase. Now let's take a look at how AWS services map into this framework. So again, moving from left to right, in the identity phase, AWS Config and Systems Manager help you identify the assets within your environment that you need to protect and those vulnerabilities that you want to build protections for. Over into the protect phase, where we're going to spend most of our time or all of our time talking about today, these are the network and security services that you can use to inspect that traffic as you're building your protection strategy for your workload. You know, all the variety of firewall services, VPC services, and the associated services to automate those techniques across your environment. And then next, as you're detecting incidents, there's a set of services we have that can actually go through event data within our environment to identify anomalies so that you can determine how to take actions on events that are of importance to you. And then next, once an incident is detected, you're going to want to automate your investigation as you get into your response phase. This is by using services such as Lambda and step functions to respond to certain types of events that are triggered via the detection phase, and that this is based off of investigative data that you can get from CloudWatch and CloudTrail, for example. And then you can build your automated response by leveraging some of our services such as Snapshot and Archive that can help you bring back your environment to a state that was previously known good. And you can automate that with AWS CloudFormation. And as I mentioned, today we're going to dive deep into a set of services that are in the protect phase or component of the NIST framework. Let's talk about some of the network protection use cases. So there's a variety of ways traffic traverses network boundaries within the AWS environment, and this helps us understand the ways that we want to deploy our security mechanisms to protect the traffic. There's three main use cases. First, there's inbound ingress, and this is traffic coming from the untrusted external internet users that are accessing your public-facing application. So basically from the outside in. Then we have outbound or egress traffic, and this is when you have trusted internal users or workloads accessing untrusted public internet resources. So the traditional from the outside or from the inside going out. And then lastly, we have lateral or east-west workflows or traffic flows. And this is when you have traffic between workloads or traffic between an internal user to another workload, for example, generally within trusted environments within your AWS and within AWS. And want to just point out that we recommend implementing the different strategies and architectures associated to these use cases independently. It offers the greatest control. It offers minimizing the blast radius. And Tom will go into some of the details a little bit later on. We do sometimes see customers combining them, and that's generally to address budget and cost constraints. Often you can reduce your costs by consolidating them with some of the other trade-offs that I just mentioned. And just to highlight, today we are going to dive into the inbound ingress use case, because when you publish that internet-facing application, the biggest concern you have to worry about is the traffic coming in from those untrusted users. But we won't dive into the details, but you should also consider what you have to take into account when that workload actually has to reach out to the internet, or when it also has to reach out to other resources within AWS to do that laterally. So we won't talk too much in detail about them. We're going to dive into the inbound ingress use case today. Now let's talk about our edge defense in depth strategy. And really what we're doing here is talking about how to combine a variety of AWS services to protect your workloads. So we start with a VPC where we're going to host our application, and we deploy that in a private subnet. And we have an internet gateway and a couple of other subnets where we can place our security controls in between the big bad internet and our protected workload. And so we're going to take a walk and a journey from left to right here in the life of a packet as it comes in from the internet and then it goes over to our private workload. So on the left side, you see AWS Shield, which is our anti-DDoS solution that is actually available for free and enabled by default to protect all of your AWS environments for workloads that we're talking about here. There is a Shield Advanced service that is available for customers that have access to response teams, so you can actually subscribe to a premium service in the Shield case. But there's no architectural considerations to worry about or take into account as you're deploying your workloads. This is an example of a service that is just that can be turned on and is transparent to your architecture and your environment. So next, take a look at some of the firewall techniques and technology that we want to apply. And so you have a web application firewall and network firewalls. And these are often used to protect different types of workloads. So your WAF will be typically used to protect a web application, whereas your network firewalls will be used to protect non-web applications. And we do see most times that we recommend customers deploy them independently, depending on the type of application you have. And then moving even further in, once we run our traffic through a firewall that can actually inspect the payload and ensure there's no malicious traffic and it's not coming from a bad source and it's going to where it should be, you want to make sure that you can load balance the volume of traffic across your workload fleet. And this is where you use AWS load balancing services. And here we're showing the application load balancer that is geared primarily for web apps, and then your network load balancer, which is for non-web apps. Again, contextualizing what type of workload you have will help you understand which load balancing technology to use, and we'll talk a little bit more about those details later. And then lastly, from a security tool perspective, you have security groups and network ACLs, or access lists. And the network access lists are a less granular, broader way to apply controls at your subnet level that allows you to say, for example, only allow port 443. And that just is another layer of protection on top of your security groups that can allow you fine-grained control to allow access between services within AWS environment, between subnets, for example. So for example, security groups allow you to reference other security groups. So for simplicity's sake, you could associate a security group to your workload, security group 2, and only allow traffic from security group 1. It's a very simple way to provide granular control of traffic between those two, that source and destination. And you can use network ACLs on top of that to put a less granular control. And for example, you could say only allow 443 traffic to come into security group, into your application load balancer, for example, into that subnet. And that would prevent other administrators from adding other services onto the application load balancer that might use other ports. So it's just another layer of protection you can add into your tool set. And lastly, there's a set of other additional services that can help you provide more visibility and more protection into your environment. We mentioned guard duty earlier, or I mentioned that. Traffic mirroring is a tool that allows you to tap into the actual network interfaces within the cloud environment to send packet layer data off to tools for analysis, detection, and response. VPC flow logs allow you to get data about individual traffic flows that are going between different network boundaries, like the different subnets, and a variety of other services that you can use to enhance your strategy. Now, let's zoom out a little bit and focus on just the security tools and think about what we need to do to make sure we choose the right tool for the job. So there's 3 different dimensions that I want you to think about this through. First is risk assessment and compliance. Make sure that we recommend working with security teams and doing a full risk assessment on the assets and workloads you want to protect. That should identify the types of vulnerabilities that you need to protect from, and therefore help you map the individual tools that you want to use to protect those vulnerabilities within your risk assessment framework. Also, in this particular category is taking into account internal compliance, external compliance, and regulatory compliance. Those different controls and requirements can often impose additional controls that you might need to put in place to meet your organizational requirements. Next, always take into consideration budget. And things to think about here is that depending on, as a result of your risk assessment, you may determine you need a particular type of tool, say a network firewall, but there are some network firewall solutions from partners, for example, that have different features available for different prices. So again, make sure that you only purchase the features that you need for a particular solution, based on what you're trying to protect from your risk assessment in your previous phase. Making sure of doing that will allow you to control your costs. And also note that the more tools that you employ adds to the complexity, which effectively means the more resources you might have to put on the task to keep the infrastructure running. and keep things compliant. So that could add additional cost to your overall budget if you have a more complex environment. And then lastly, take into consideration the deployment model for your particular environment. And this is important and because there's two broad deployment models that we typically see deployed, that we see implemented in the AWS environment. That's the distributed model, where you aggregate the securities, or distribute, I should say, the security services to all of the VPCs that you have, where you have workloads or users deployed. That allows you to, reduce your blast radius and distribute the controls. And there's also a centralized model that allows you to centralize all of your controls and services into a central VPC, for example, to simplify some of your controls. And Tom is going to go into details on the different deployment models and the considerations there. And so speaking of Tom, let's pass it over to Tom so he can jump into our foundational constructs. Tom, take it away.
Thanks, Nick. So at this stage, you should probably already know what type of firewalling solution you need. And before we dive into the specific architectures for the different firewall types, I want to spend some time recapping some of the foundational constructs that are relevant to understand the upcoming architectures. And I want to start with load balancing, and there's three different categories that we'll look at. Start off with Amazon Certificate Manager. So Amazon Certificate Manager is a managed service that allows you to generate public certificates and then assign them to AWS managed services, things like application load balancer, CloudFront, API gateway, and so on. The good news with ACM is that if the certificate expires, it gets automatically renewed and then automatically updated on all of those managed services. The bad news is you can't export the certificates generated in ACM. So if you want to assign a certificate to your third-party appliance that would need to have the same certificate as your load balancer, and you'll see scenarios where that might be needed, you can't actually generate that certificate in ACM and push it to the firewall. That's not something that's possible. A workaround is to generate a certificate outside of ACM. So have a separate place where you generate a public certificate, and then that certificate can be imported into ACM, and from there assigned to the AWS managed construct, like application load balancers and CloudFront, and then separately you would import that certificate onto your firewall. Now, another construct I want to touch on is target groups, and specifically target groups for application load balancer. So if you're exposing your application to the internet, you would usually use a load balancing construct. So application load balancer is the most common for your web applications, and it supports different types of targets. So you can target an EC2 instance or a container. You can target a Lambda function. So this is effectively your pure code running in a serverless mode. And then you can target an IP address. What you can't target is another load balancer. So there might be scenarios that will show in the future that require you to point from one application load balancer to another application load balancer. You can't do it natively. The reason for that is that application load balancer has dynamic IP addresses that constantly change. So there's no easy way to natively connect the two. If you do need to point from one ALB to another ALB, you can do that through integrating with network load balancer. So there's a native integration where you can put a network load balancer in front of application load balancer. Network load balancer supports static IP addresses that never change. So then you can point to an IP address and effectively achieve this flow. Another option would be effectively putting a third-party proxy on an EC2 instance. That's also something that you can do to be able to target one ALB with another ALB. And finally, I want to explain the concept of proxying versus bump in the wire, which applies to the different load balancing technology that we will be discussing. Application load balancer is effectively a reverse proxy. So if we have a user connecting to an application load balancer, they would be targeting explicitly that application load balancer. The application load balancer terminates that connection and then initiates a separate connection to one of its targets. So it's doing its job, load balancing, but also proxying. With gateway load balancer, we have a user connecting to some destination, and that destination could be an instance, but it could also be another load balancer. However, the gateway load balancer doesn't act like a proxy. It's completely transparent, and you have to route traffic to it. We'll show some examples in a second. And that way you can effectively transparently insert a security function into your flow between any source and destination. And I'm showing here the user is the client. It could be another application that's generating this traffic. And another set of fundamental concepts I want to touch on are related to VPC routing. We will be using VPC routing quite a lot in the architectures I'll be showing you in a second. So it's good to have a quick recap on what are the different routing options inside your VPC. So I want to start off with per subnet routing on the left. Each subnet inside a VPC can have a unique route table. So you can have multiple subnets share the same route table, and that could be fine. But you might have requirements where one subnet needs to have a different route to another subnet. So in this example, we have subnet 1 with a default gateway via a transit gateway, or default IPv4 path effectively via transit gateway. And then we have subnet 2 with a default route via internet gateway. So these are two different destinations for the same route. And you would typically use that if you want to have a different behavior for the resources living in your subnets. And you'll also notice there's a local route that's added there by default. You don't have to do anything for that local route to pop up. It's always representing the CIDR that you've assigned to your VPC. And that effectively states that anything within that CIDR, so all of the subnets within the VPC can communicate to one another. So they can have full-on reachability, even though they're in different subnets. So that's concept one. Remember, if you want to have different routing behaviors, create different route tables for your subnets and then assign them to different subnets. Therefore, your resources in those subnets will have different routing. The other concept I want to touch on is ingress routing. This is specifically for where you're using different gateways. I'm using internet gateway as an example, but a virtual private gateway is applicable here as well. So with ingress routing on the internet gateway, what we're effectively doing is creating a route table that's assigned to the internet gateway. And what we're saying here that instead of sending traffic to the destination subnet, subnet 2, where we might have some resource, maybe a load balancer on EC2 instance or a container, we don't want that traffic to go directly to subnet 2. We want to redirect that traffic through some network interface, maybe a security function, maybe a monitoring function inside another subnet. So this is a little bit like a redirector route. So traffic coming in just redirects through this network interface and then hits subnet 2. And then we need to make sure that return traffic also goes back the same way. We don't want to have a situation where traffic ends up being asymmetric. So we see here that the ingress route is forcing traffic through this ENIX. So this is just a network interface. And then subnet 2 route table is returning the traffic to the internet also through ENIX. And then finally, when ENIX is done with the traffic, it can just use the regular VPC routing to either send it to subnet 2 or send it out via IGW. And the final construct within routing inside of VPC I want to touch on is more specific routing. And this is a little bit counterintuitive because more specific routing from the on-premise world is just routing, right? Normally, if you have a more specific route, that's preferred over the more generic route. In the context of VPC, the generic route is the local route. And until more specific routing was launched, you had no ability to override the local route. So if you wanted to influence the traffic between different subnets in the VPC, you couldn't do that. But with the launch of more specific routing, you can. And let's add a network interface here that will be pushing the traffic through. Again, this could be a firewall, and we will see some examples later on. But think about it as just a representation of any kind of service that we want to push the traffic through transparently. And then in subnet 1, what we'll say is if you're going to subnet 2 IP address block 10.0.2, go via ENIX, right? And then on subnet 2, when we're returning the traffic back to 10.0.1, we also will go back through ENIX. So any traffic flow between subnet 1 and subnet 2 is now forced to go through ENIX, and we can deploy whatever we want behind ENIX. Okay. Moving on closer to the architectures we'll be discussing, I'll spend some time showing you the different deployments for your security solution, both in the distributed model and the centralized model. So to explain distributed ingress, and by the way, we're focusing here only on ingress. The distributed ingress is where you have an internet gateway assigned to each one of your VPCs, and each VPC has its own kind of internet connectivity stack. Centralized ingress is if you don't want to deploy the internet gateways on all of your VPCs, you want to keep them isolated, and you want to create this central funnel point, central VPC through which traffic is going to come in on, and then will be distributed out to different VPCs. And there's different mechanisms to do that, so I'm not showing anything in the middle there, but we'll see in a second what those different options will be. Now the question is, should I centralize or should I not centralize? That's I hear that from a lot of customers. The pros of centralizing, it is simpler to control your internet access, right? So usually the very security conscious customers are the ones that are worried about their ability to control a large number of VPCs and making sure the IAM policies are correct and having config rules to detect any misconfigurations. Some customers feel it's easier to create a centralized ingress. However, there are some cons of that deployment, right? So first of all, we're increasing a blast radius. Because you're going through the central VPC, maybe a central load balancer, and then other construct, potentially misconfiguration in any one of those constructs can impact multiple things. Where before, if you had individual internet stack for each VPC, you didn't really have to worry about that. You also have potentially increased complexity and increased cost, right? Because now you have traffic going through more components as it's going to its final destination, where with a distributed model, it's going directly. So typically, what we recommend is if you can go with the distributed model, but it's also understandable that if you feel like this is a solution that fits your requirements better, centralized is also an option. And I will show you examples of both approaches for all of the firewall solutions that we'll be discussing today. Okay, so let's dive into the network architectures. And we'll start off with Web Application Firewall. This is an AWS managed service that allows you to inspect your web applications. It's purely designed for web applications. It allows you to do IP address blocking. It allows you to do rate limiting. It allows you to apply mitigations against things like cross-site scripting, SQL injection, web-specific attacks. You can create different policies, and you can deploy WAF on a number of different AWS managed constructs like CloudFront, Application Load Balancer, API Gateway, and AWS AppSync. In the diagrams, I'm going to only show you the CloudFront and Application Load Balancer deployment today. All right, so if we start with a distributed model, which means we'll have one VPC, but imagine this VPC multiplied however many times you need it. So maybe you have multiple teams, multiple applications, you create dozens or hundreds of VPCs. Each one would have the same model. So here we have an application load balancer pointing to some targets. Now, I'm showing you EC2 instances. These could be containers, these could be Lambda functions, any other supported constructs that the load balancer can target. And then we deploy WAF on the load balancer itself. And again, load balancer is specific for HTTP and HTTPS applications. It terminates TLS. It has to terminate TLS. So it also means that it allows AWS WAF to inspect the unencrypted traffic. So you can do deep packet inspection on the payload, and then only if you're happy with the traffic, forward it to the target. And application load balancer can re-encrypt the traffic again and send it back to the target, or you can send it unencrypted. We typically recommend that you keep the encryption going all the way. If you're planning to manage this in a centralized fashion, you can use Firewall Manager. It's a service that allows you to orchestrate different firewall and security configurations. We'll dive a little bit more into it a little bit later, but effectively think about it as a way to create a policy in a central place and then apply this policy on the load balancers and WAF configurations across a set of accounts in your organization. So you could say, I want this WAF policy to live on all application load balancers that have a tag production in my organization, and then that particular policy goes out to all of them and is enforced. The other option, you could put WAF on CloudFront. So CloudFront is a content delivery network. If you're running web applications, you usually, and you care about performance, you would usually look at content delivery networks to front end your web application. And you can also deploy WAF on CloudFront. And it's a common approach to have WAF on CloudFront as well as on the application load balancer. The WAF on CloudFront is running in all of our CloudFront POPs, where we have over 200, I believe, right now, where traffic can be stopped at the entry point. And then the application load balancer could just run WAF to look for particular headers that maybe your cloud distribution is adding, just to make sure that traffic only comes from your CloudFront distribution. Yep, traffic come in, it hits the CloudFront, terminates, TLS is terminated on CloudFront, WAF is applied, traffic is re-encrypted, sent to application load balancer, terminated again, WAF is applied, then re-encrypted again, now with a private certificate, and sent to the EC2 instance, or a container, or a Lambda function. So what about the centralized model? So as mentioned earlier, a centralized model is where you have a set of VPCs. They don't have their own internet gateways, but you will create a central entry point and then connect those VPCs to it somehow. So the first model is when you would use a transit gateway. So transit gateway, think about it as a logical router. It's a distributed system. So itself, the transit gateway doesn't have, it's not a single point of failure. It doesn't have an aggregate bandwidth limit because it's not a single object. You have to think in terms of attachment. So each attachment to a VPC can do up to 50 gigabits a second. And effectively, this is a highly scalable distributed system allowing you to connect different VPCs. So you connect your VPCs through transit gateway, and then you create the edge VPC where you have your application load balancer running WAF. And then, as mentioned before, application load balancer cannot target another application load balancer. So that's why in the application VPCs at the bottom, we are using network load balancers. Right? We could put another application load balancer behind that network load balancer, just like I shown earlier, or we could put a proxy inside that edge VPC to make it work and allow application teams in the application VPCs to just create ALBs. As traffic comes in and hits the application load balancer, it gets inspected. Application load balancer can do host or path-based routing. So we'd look at the host and say, okay, this particular host name is NLB in VPC1, and it will forward the traffic for the transit gateway. So transit gateway effectively creates this routing connectivity between our VPCs. Another way to connect your edge VPC and your application VPCs is to use a construct called private link. So think about private link as a way to expose just a particular port on your network load balancer as a network interface in the edge VPC. It's a one-directional communication, so traffic can only come in from the edge VPC down to the NLBs and application VPCs. You can't initiate connections from the app VPC. So it's a very surgical way of exposing an individual port, individual service, versus transit gateway being more of a, I'm opening up my network and then using things like security groups and NACLs to limit things. So as the traffic comes in, it hits the load balancer like before, we apply our WAF, and then we forward traffic to the appropriate VPC endpoint, and then that traffic is powered by private link landing on the NLB and effectively forwarded to the target destination EC2 instance or container. Okay. So moving on to the next construct, and this is where you can bring in your own appliance into AWS. And it used to be pretty tough to do that. You had to think a lot about availability and scale and often build your own automation for Lambda to actually make it work. We made it super easy with the launch of Gateway Load Balancer. So Gateway Load Balancer is this bump in the wire load balancer that allows you to transparently insert any virtual appliance into the traffic path. Right, so in our example, we're talking mostly about security appliances, effectively firewalls, but customers have also used it for traffic mirroring and other use cases to inspect the traffic. So here's a set of partners that already have integrations with Gateway Load Balancer. So if you are already working with any of those vendors, it's actually very easy to bring their appliances into AWS and put them behind the Gateway Load Balancer to insert their security function anywhere in your network. Okay, so let's see how we are adding those security functions into the network, into our distributed VPC first. So we're back to having a load balancer, and this could be a network or an application load balancer. So I'm just using the generic name Elastic. And it's pointing to some targets. Again, these targets could be anything. And what we want to do is we want to inspect traffic before it hits the load balancer. So first thing we do is create a VPC with a gateway load balancer pointing to the set of third-party firewalls. And again, pick one of the vendors that I showed you earlier, put them behind the gateway load balancer so that it can forward traffic to it. And then the way to present a gateway load balancer into a VPC is through endpoints. So similar to the private link endpoints, it's effectively an extension of that load balancer, but it's not a proxy. So traffic sent to the gateway endpoints, it's transparently navigated to the gateway load balancer, then to the firewall, and then back to the endpoint so it can continue to the Elastic load balancer. So think about anytime the traffic hits the endpoint, you're applying your security function. So all you need to do is just make sure you configure routing to send this traffic appropriately. So we already learned about the ingress routing. So here what we would say is that if the traffic is destined to the elastic load balancer, which we know is subnet 3 and subnet 4, that would actually be the specific IP range of that subnet, it should be sent via the appropriate gateway load balancer endpoint. And then we need to make sure that the return traffic doesn't go out directly through the internet gateway, but it also is being sent through the gateway load balancer endpoints. And then finally, we need to make sure that the gateway load balancer endpoints themselves have a route back to the internet. Obviously, I'm ignoring subnet 5 and subnet 6. Routing here is kind of irrelevant, and it's fine with the local route. And I'm also not showing the local route here. We already know that the VPC is always going to have a local route in all of those subnets. So any application type is supported with this model, depending on what you configure in your firewall. TLS decryption, again, also dependent on the firewall. And then that will also determine how deep into the application you can go, right? If you can't decrypt the traffic, you can't really do more inspection than layer 3, layer 4. Data plane, again, this is distributed. So the way you would manage this centrally is usually through your favorite vendors' centralized tools. So different vendors have different tools to manage firewalls at scale. The good news here is you only need one VPC where you have your gateway load balancer and a fleet of firewalls. And all you need to do is put endpoints into different VPCs instead of having to recreate the firewalls or the gateway load balancer. So another option is to put your security function in a slightly different place and use the more specific routing capability instead of the ingress routing. So this is not supported with network load balancers and instance targets. So load balancers, as I mentioned earlier, could be targeting an instance, could be targeting an IP address. If you're targeting an instance from a network load balancer, you can't use more specific routing to insert a security function there. But if it's an application load balancer, or if it's a network load balancer with IP targets, you're good to go. So instead of putting the gateway load balancer endpoints between the internet gateway and the elastic load balancer, we're putting it behind the load balancer, between the load balancer and the targets. We need to configure more specific routing to ensure that when traffic hits the ELB and it tries to go to subnet 5 and subnet 6, it actually gets redirected through the appropriate endpoint. And then on the way back, we need to ensure the same. So if I'm returning traffic to the load balancer, I will be sending it through the appropriate endpoint. And traffic flowing through hits the load balancer first, then the endpoint, then the gateway load balancer firewall, then back to the endpoint, and then to the destination. Return traffic flows exactly the same way. So you might have a question on why and when would I use which model, right? Should I use ingress routing and put the firewall above the elastic load balancer, or should I use more specific routing and put the firewall below the load balancer? And again, remember, you can't do the more specific routing with NLB and instant targets. So the approach on the left, the good news is the firewall will see all traffic, right? So any traffic sent to the elastic load balancer can be seen by the firewall, which is good and bad. It's good because then the firewall can see all of the traffic. It can also see the client IP address in the packet. The bad news is that typically a load balancer would listen on a particular port, maybe 443. If it's an application load balancer, it will drop all other traffic by default. So you don't really need to have a firewall in front of a load balancer, dropping UDP or TCP that's not port 443, that gets dropped by default. So your firewall potentially is doing a little bit more work here. And in cases of when you see a DDoS attack, you may have to scale your firewall layer before Shield Advanced kicks in, or Shield kicks in. You also here need a public certificate to decrypt TLS, right? Firewall is in front of the ELB, so the public certificate lives on the load balancer, and you also need that same public certificate on the firewall, which means you can't use ACM to generate certificates. You can use ACM to host certificates that are generated somewhere else, but you can't generate them and then export them to the firewall. With more specific routing, the firewall loses some visibility, right? It's only seeing traffic that's already been accepted by the load balancer. So it means it doesn't have to deal with any traffic that's not legitimate directly hitting the load balancer, so different ports, different protocols. But it also means that it's losing visibility of the real client IP. So the elastic load balancer in this scenario will hide the IP address and change it, the source IP address, to its own IP address. So if you want to apply some policies on your firewall, you will have to do that on things like maybe HTTP headers, like X forwarded for, if your traffic is coming through an application load balancer. And finally, from a certificate standpoint, between the ELB and your target, you would usually use private certificates. So you no longer have to assign a public certificate to the firewall. It can be just a private cert that you're using on your targets. Okay, let's talk about centralized architectures. They're actually pretty intuitive. All we're doing is we're moving out the backends to another VPC. So you can imagine how this is going to look like. We have our edge VPC with gateway load balancer endpoints. I'm not showing the gateway load balancer VPC anymore, but imagine it's there on the side with all your firewalls. Then we have a load balancer that's public facing, and then traffic is being sent through the transit gateway to the actual destination. We also support the private link model, same exact scenario. Ingress routing redirects the traffic to the load balancer. Then the load balancer sends traffic to the private link endpoints, and those private link endpoints send traffic to the NLP and the target. So pretty straightforward. We support the same exact scenario with more specific routing. We're just reversing the order of where the firewall lives and where the load balancer lives. So now we have the load balancer first, and then the firewall function second, and traffic coming in hits the load balancer first, and then the security function before it's getting forwarded through the trans gateway to the app VPC. Again, I'm not showing you the route tables here, but you obviously need to go in and configure each individual subnet route table to make sure traffic is symmetric and traffic is flowing accordingly. With private link, same exact scenario, rotating the order, ALB first, gateway load balancer second. Now, we had a recent launch, a joint launch with Palo Alto of Cloud Next Generation Firewall. So Palo Alto, you may have noticed, is one of the vendors that supported gateway load balancer from the original launch. So now with this launch, they're actually giving you the ability to provide a managed service. So you see here the gateway load balancer, the Palo Alto VM series, exact same architecture like with a gateway load balancer, but now Palo Alto is managing that VPC. So you're still configuring your routes just like you did with gateway load balancer to make sure the traffic hits the load balancer endpoint. But you don't have to worry about managing that gateway load balancer VPC or firewalls. It's just all managed for you. And all you need to take care of is making sure you put the endpoints in the right place and then configure the routing. And there's a number of ways you can do that. So you can use the AWS Firewall Manager. So I called out Firewall Manager a little bit earlier when we talked about WAF. It's a way to centrally configure policies and distribute them into services in your account. So you can also use it now for configuring Palo Alto Cloud Next Generation Firewall. And you can pick which particular deployment model you want to do. So if it's distributed or centralized, and it can also be used for other traffic directions. Today, the session is focusing on Ingress filtering, but we also have egress, east-west, all of those other traffic flows are supported. And at the same time, you can use the web interface on the Palo Alto, their cloud portal, to either supplement what you're configuring on AWS or actually completely configure your firewall there. So you have a lot of options, as well as the options at the bottom, allowing you to use APIs and Terraform and CloudFormation, all of the tools you might be already using for other services. Okay. And I want to touch on a network firewall. So you can think about a network firewall as an AWS managed firewall offering that is also powered by gateway load balancer. So under the hood, network firewall is powered by gateway load balancer. It's using a Suricata engine. So it's if you're familiar with open source Suricata, it's using that language to configure policies. So you can create your policies, decide what you want to do with the traffic, do your monitoring. And again, just like Palo Alto Cloud Next Generation Firewall, or just like WAF, you can configure network firewall through Firewall Manager centrally and distribute your policies across your different accounts. And because it's powered by gateway load balancer, you'll notice that the architectures are looking exactly the same, like the ones I showed you with gateway load balancer. But now you don't have to manage that gateway load balancer VPC or any kind of firewalls behind. That's all a managed service. So all you need to do is deploy the network firewall endpoints, configure your routing, and then traffic is going to come in and be redirected through the network firewall before it hits the load balancer. One thing to note is today network firewall doesn't support TLS decryption just yet. So it means that it might be limited in terms of what you can inspect, right? Often with ingress scenarios, you actually do want to do TLS decryption to see what's exactly in the traffic, especially that you often own the certificate. So that could be a limiting factor here, at least for now. However, if at any point the traffic is decrypted, then network firewall can actually apply IPS policies on the application layer. And just like mentioned earlier, management all centralized through the firewall manager. You can also do more specific routing, just like with Gateway Load Balancer. So I'm not going to spend too much time on this, but you already know how this works. Traffic comes in, hits the load balancer, and then more specific routing forces it through the firewall after it's hit the load balancer. Return traffic also uses more specific routing to go through the network firewall. Centralized models, exactly the same like with Gateway Load Balancer. We can use either ingress routes to send the traffic to the firewall in the edge VPC before it hits the transit gateway in the application VPC, or we can also deploy the same model but using private link instead of the transit gateway to expose our applications to the edge VPC. And same as before, more specific routing is also available here in the centralized architecture. Just the order is reversed. Okay. And the final model I want to talk about is ELB Sandwich. An ELB Sandwich, or Elastic Load Balancer Sandwich, is a solution that's been available pre-Gateway Load Balancer, pre-Network Firewall, and it's been a common pattern for customers before Gateway Load Balancer got launched. It's still a valid solution for ingress, inspecting your ingress traffic. And the way it works is you would have an internal load balancer pointing to your target. So it's no longer a public-facing load balancer like we had in the previous examples. It's a completely private load balancer. And then you have an internet-facing load balancer that points to the third-party firewalls. However, in this scenario, the third-party firewalls are actively participating in forwarding the traffic. So you would usually send traffic to the third-party firewalls on a particular port, and you have to configure those third-party firewalls to then forward traffic from that port to the appropriate internal load balancer. Most vendors can do TLS decryption in this scenario because the firewall is explicitly participating in the traffic. And from a management standpoint, again, you have to look at your firewall vendor to figure out how you would manage firewalls at scale. The distributed model, however, is not that popular for this particular scenario. So with all the other deployments I mentioned earlier, Gateway Load Balancer, Network Firewall, and WAF, we would recommend you go with the distributed model because that has more benefits and less downsides. With ELB Sandwich, it actually gets very costly if you start deploying this pattern across multiple VPCs because each VPC actually has to have its own set of firewalls. So that's where the most of the cost comes in. So centralized models are actually very similar. We're just moving the second part of the sandwich, the bottom load balancer, down to an application VPC. And you'll notice here something interesting. In the application VPC, now we can have an application load balancer or a network load balancer. The reason for that is the third-party firewall can often forward to a host name. Again, you'd have to check that with the firewall vendor of your choice, but many of the firewall vendors can translate from a port they receive the traffic on to a host name in the backend. And because they can use a host name, they can point to an application load balancer, which has dynamic IP addresses. So it effectively is a way for you to not have to force the application VPC to present you a static IP address first through an NLB. You can just set up an ALB in the VPC and forward traffic to it from the third-party firewall. We're on the right-hand side with a private link endpoint. We have to use NLBs. NLBs are what powers private link and what allows you to deploy private link. So you would have to use an NLB in the scenario on the right-hand side. Okay, so I want to spend some time quickly recapping the differences between the ELB sandwich and the Gateway Load Balancer transparent deployment, just so we're clear on the same page. So let's start with the ELB sandwich on the left. We can see the sandwich. We have the internet-facing ALB, we have the internal ELB, we have the firewall in the middle, and then we have a user and the destination at the bottom. So when the user, and we'll have a look at what's happening with the IP packet through every stage of the forwarding. So if the user connects to the internet load balancer, the source of the packet is the user IP address. The destination is the internet-facing ALB IP address. Then the ALB will actually translate the source to its own IP and forward it to the IP address of the firewall on a particular port. And that's where you have to configure the firewall for every application. You have to decide which port the firewall is going to be receiving traffic on and what host name it needs to forward that traffic to. Once the configuration kicks in, the firewall decides where to forward it. It then replaces the source IP address with its own IP address. So it's doing source NATing, and it's forwarding it to the appropriate internal load balancer. And finally, the internal load balancer is replacing the source IP address again, and then forwarding to the destination instance. On the way back, the flow is reversed. So how does that compare with gateway load balancer? A user connects to the load balancer first. That's exactly the same. And by the way, this model I'm showing you is with more specific routing. But if we were using Ingress routing, the firewalling function would be already kicking in. But this is more specific routing. So the firewalling is after we hit the internet-facing ALB. And what happens then? So the internet-facing ALB will swap the source IP address to its own IP address, but will have the EC2 instance as the destination. And then gateway load balancer in any firewalling is completely transparent. So you don't have to configure your firewalls to understand what ports the traffic's coming in on or what destination to forward it to. All you need to do with your firewalls is then configure what policy you want. So what traffic you're allowing, what traffic you're denying. You don't need to configure any forwarding or NATing rules. Okay, so putting it all together, as Nick said, when you are deciding on your security policy, align it with some security framework, and NIST is a particularly good example. Always perform your risk assessment, right? You want to figure out exactly what functionality you need to cover your risks. What controls do you require? I see a lot of customers putting firewalls just because, and then you have to think about the reward you're getting, so the benefits you're getting from putting a particular firewalling function, and the cost, right? Because you're spending money on it. There's operational overhead, there's complexity. So always understand what requirements you have and make sure you're not just putting things into the environments just because you think they have to be there. And then consider the budget and review the available architectures we just covered. Hopefully they'll be helpful in helping you decide which solution to go for. And with that, I want to say thank you for your time and goodbye.